All right, thanks so much, everyone. Welcome to the webinar. Thank you so much for joining us. I'm excited for our data science team to lead today's webinar. If you could jump to the next slide.
Yeah.
My name is Sabrina Oden. I'm the market strategy manager here at Recurve, where I help clients unlock the benefits of demand flexibility, build market-based programs, and transform their data into actionable insights for program design and grid planning. Joining me is Adam Shear. Adam has more than 10 years of experience in energy efficiency, renewable energy, and biofuel research. He is an expert in energy efficiency evaluation, implementation, and policy. Of note, Adam led the incorporation of smart meter data analytics into PG&E's energy efficiency portfolio, where Adam and I used to work together. Also joining us is Armin Aligolian. Armin joined Recurve in June 2022 as a data scientist. Prior to, he got his PhD in electrical engineering, in which his main research area included power distribution systems, time series analysis, anomaly and event detection and clustering with deep learning models and optimization techniques. In line with his research area in academia at Recurve, he develops methods on electric vehicle detection, solar panel generation disaggregation, and energy forecasting from electricity meter data, which we're going to dive into in a bit. Next slide. I wanted to share a bit about who we are, and then we will dive into the presentation. For those who don't know, Recurve was founded in 2015 with a mission to accelerate the transition to a clean energy grid through flexible demand-side resources. We connect the dots between efficiency, electrification, renewable energy, and distributed energy resources to enable demand flexibility to become a market-based procurable resource. Why did we want to have today's webinar? New technologies are impacting customer-level energy consumption, and they have epic grid reliability implications. Rooftop solar PV installations are expected to triple by 2030. Electric vehicles will account for more than 30% of light-duty vehicle sales by 2030. And by 2050, transportation electrification loads could account for more than a quarter of global electricity demand. While these new loads can be advantageous to the grid and help us to decarbonize, they can make emissions and grid reliability worse. We are seeing a massive need for demand flexibility and virtual power plants. Recurve is in the process of producing and facilitating virtual power plants. A critical aspect of this, as hopefully you all know, is measurement. We have to be able to measure all these new DERs holistically, along with energy efficiency and demand response. We are digging into these issues and want to get a sense from you how you see the world and how we can solve these challenges together. And now I will pass the mic to Adam Shear, our VP of Applied Data Science.
Thanks, Sabrina. And thanks everybody again for joining. I think we're going to have some fun today. This probably won't be like the most polished and, just kind of rote webinar you've ever seen. And hopefully that's a good thing. We're going to dive into some new R&D that we've been doing. And actually, we're going to kind of pull back the curtain and give you a peek into elements of these modern methods that I think are going to be critical in the long term, but we're just in the nascent stages of trying to figure out how to actually go about solving some of these problems in a holistic way. Because as Sabrina mentioned, there's a lot going on the grid. I'm sure that's why you're all here and why this industry is exciting right now. So we're hoping to leave some time for discussion as well, to get ideas from you, feedback from you, talk about ways that even we could potentially partner, because I guarantee you we're not the only ones trying to figure these problems out. And one of Recurve's kind of core modes of operation for a long time has been open sourcing a lot of what we're doing. So a lot of what Armin is going to talk about today are the precursors to new open source code bases that we're hoping to develop in the next couple of years. So we'll get into all of that. We're going to start with some background. I lead the applied data science team, so I get the privilege of just kind of setting the table and letting the folks who do the real work do the talking, which is going to be Armin for the latter half of the webinar. And then we're going to talk about some new methods that we've been developing, Armin specifically, that utilize deep learning methods, neural networks on both the solar PV disaggregation front, which is a problem that, as we've looked into the literature, we've realized nobody's really solved this yet in a comprehensive way that can be applied to millions of meters, which is the scale that we need demand-side resources to be operating at right now. And EV detection, which is an early stage sort of project where we want to be able to help utilities find who has an EV so that those utilities can understand which programs they should be marketing to those customers to get them to charge at the right times of day in order to make them grid resources instead of grid liabilities. So we'll talk about both of these things and some of the methods that we've been developing internally at Recurve. And then we're going to open it up, hopefully, for some discussion, and hopefully folks have some thoughts they can share, or even if it's just to say, hey, we're seeing those problems too, it would be good for us to get that confirmation. So just to get started with the lay of the land, what's happening out there? Why are we interested in these problems? Well, 10 years ago, even the electric grid kind of was a dinosaur, right? And this, you've heard it many times before, but the electric grid kind of was the same. It looked and felt and operated the same way that it did 100 years ago, where basically utilities tended to solve most problems or almost all problems with supply side answers. But as we've come into the modern era where we have to solve climate change and we need big solutions on the demand side as well as on the supply side, the electric grid is being asked to do things, even though the technology on the grid itself is kind of slow to evolve. That same grid is being asked to balance renewables, which are more intermittent. They are more variable. We've all heard this before at this point, right? If the sun doesn't shine, you don't get solar power. If the wind doesn't blow, you don't get wind power. We need to balance those renewables. The electric grid also needs to facilitate building electrification. So if we want to decarbonize, we can't be burning old dinosaurs in our homes in order to heat our homes and to heat our water, and to heat our pools and our dryers and our stovetops and all these kinds of things. So we need building electrification. We need that at scale. That means that the electric grid is going to be seeing new demand. And that new demand is not necessarily going to occur at all hours of the day equally. So we will expect new peaks from building electrification. We have transportation, right? All of a sudden, the electric grid itself is going to be responsible for decarbonizing transportation, ground transportation specifically. And that's something that I'm not sure if we've all fully wrapped our heads around what that means and how we're going to be able to facilitate this massive new load that the electric grid is going to have to conquer. And all of this, again, is related to decarbonization. That's why I'm here. I presume that's why many people are here, is we want to work on this problem. We want to work toward a sustainable future. These are the elements that are going to get us there, hopefully, at least in part. And they're all need to plug into the electric grid. So Sabrina already mentioned this, solar PV has been around since like the days of the Carter administration or whatever. We put solar PV on the White House rooftop. And so it kind of can seem like, well, this is an old story. But in reality, rooftop solar PV is slated to triple by 2030. There are still new incentives coming out that are richer. The technology is still evolving, becoming more efficient. And these are just examples of headlines we found with very quick, Google search, looking at the rise of solar PV. And in a very real sense, even today in 2023, we're still at the beginning of that exponential rise of solar PV. And in addition, solar PV is adding in places where there is a lot of grid level solar as well as solar PV. This is an example of how the net demand in California is looking during days where there isn't a lot of heating, not a lot of cooling, so there tends to be low electricity demand. We're already starting to see that the renewables are outpacing total consumption at times on the grid, and this trend is expected to continue. Along with that midday dip because of solar PV generation, we're also seeing this huge rise in the evening, this evening ramp. And this is creating problems for utilities to forecast their load accurately. It's creating more risk. It's creating more issues with how do we actually shift this load around so we can actually take advantage of when we have a high penetration of renewables on the grid. So everybody has probably seen this at this point. This is the duck curve, and there's all these jokes about, well, maybe it's actually the giraffe curve now. But this is very real. And if you're outside of California and your state or your jurisdiction is looking to install lots of grid level solar, that works for a while. But we're at a point in California right now already where we are curtailing more solar PV and wind generation than the entire energy efficiency portfolio that costs $1 billion a year is saving. So this is a very real issue. We have to find ways of shifting this load around. And on top of all this, as I mentioned, there's electric vehicle adoption. So we're talking about more than 25 million electric vehicles that will be on the US roads by 2030. That is going to that's going to result in more than a 30% increase in residential electricity demand. New peaks, when are people charging? Are they actually responsive to time of use rates? Or do they need, definitive programs to encourage them to charge during times that are low in carbon and that are, less costly on the grid and cause less reliability issues on the grid? Right now, a lot of time of use rates that encourage EV charging encourage that charging at night. Well, at night just so happens to be also the time period where carbon intensity tends to be highest. So do we want to charge our EVs from our coal-fired power plants, or do we want to charge those EVs from solar power? Utilities are going to have a big hand in that, in how they design rates and how they design programs for these customers. Do utilities even know who has an EV? That's actually a question we're kind of hoping folks might weigh in on and give us some insight into here in this webinar. We believe right now that we understand right now that when a customer gets a solar, there's interconnection communication that has to happen with the utility. There's a lot that has to happen in coordination with the utility. That utility knows who has solar. They know usually when that customer purchased that solar panel and installed it on the rooftop. I'm not sure that that's analogous in the world of an EV. We purchased an EV last year. We didn't have to notify our utility that we had gotten an EV. And how to, like I said, connect these customers, these EV customers, to programs so that we can ensure charging happens at beneficial times instead of times that are liabilities to the grid. Obviously, all of this is this balance between supply and demand. And up until, like I said, maybe 10 years ago, this was an equation that tended to be solved almost exclusively through supply side resources. So if there was a load constraint on the grid, you could address the grid itself potentially, or you would build more fossil fuel generation if you were a utility, bring on a new natural gas power plant. But anymore, those solutions that add carbon to the equation just are no longer tenable. And I can't even imagine what it would be like in California, as an example, if PG&E or SCE said to the CPUC, hey, we're going to install another natural gas power plant. I can't even imagine how that conversation would play out. It's a non-starter, right? So we really have to figure out how we bring the demand side into this equation in a way that is legitimate and is powerful. And that's really what Recurve's mission is, as Sabrina mentioned. Already we're seeing on the California grid large swaths of rolling power outages and things like this. And as heat waves and as the impacts of climate change become more severe, we're going to see more of these kinds of scenarios where all across the state of California and even into Nevada, Arizona, Las Vegas, the Mountain West, we have load constraints on the grid. We have price spikes. This was a screenshot that I took a couple of years ago during a heat wave in California, where every single one of those maroon dots across the entire grid represents a node on the grid where there's specific pricing that can be tracked by the California Independent System Operator. Every single one of those dots was above $1,000 a megawatt hour. And we're seeing price spikes of up to $6,000, $8,000 a megawatt hour. That's creating A, reliability issues, B, massive costs that customers eventually have to cover. So we're asking ourselves, can we bring genuine demand flexibility to the table to help alleviate these kinds of circumstances, but also even under days where there aren't price spikes, can we spread out that renewable generation into areas of the day that are high in carbon intensity, but aren't necessarily causing price spikes? So one of the ways that this is happening in California right now are through these market access programs. If you haven't heard of these programs, or you're from outside of the state, this is something I would encourage you to read up on, because we're seeing a lot of excitement behind this kind of a model where because we are measuring savings at the meter, and we're not using sort of pre-estimated deemed savings values that need to be evaluated and accounted for later on down the line. And we have an hourly measurement. So we can say very shortly after the program operated, this is what was saved. Here's how you can forecast it for next year. This is when the savings occurred. We can connect directly that measurement and the dollar value of what the savings were worth to a payment to an aggregator or an implementer who is actually running the program. So we're having aggregators come to the table saying, I have this type of a program. I'm serving residential customers with smart thermostats, and we can program those thermostats and we can get them participating in event-driven savings. And I also can bring to the table energy efficiency into that equation. So I can also make that air conditioner run more efficiently because I have a maintenance program or whatever it is. This type of model allows aggregators to come to the table and say, hey, this is how I serve customers. And there's not necessarily a technical program manual for it. There's not necessarily a work paper that dictates what I can get paid and what the savings are or anything like that. But because we can make a measurement of what the savings are, when they're occurring, how much it's worth to the utility, then we can assign a payment to an aggregator, and we can say to a procurement planner, this is why you can count on this program. We have a meter-based measurement. Here's why you can trust it. And all of this is it basically takes place with this kind of a measurement scheme. So we're just looking at what we call a baseline period, where we have how the customer is using energy before a program. And then we have, with that baseline period, we create a model of each individual meter's energy consumption. And then the program actually takes place. So maybe you're installing a new air conditioner, or you're installing new lighting, or you're installing a smart thermostat, whatever it is. There's a time period where there's a change happening in that building. And then afterward, the building has a new operating paradigm. And during that post-program period, we use the baseline model and we project it forward as what we call a counterfactual. And that counterfactual represents the energy that we predict a customer would have used if they had not participated in the program. And that counterfactual allows us a comparison between what the customer actually used after the program and what the prediction was. The difference between those two things is what we can assign as the savings. And this type of measurement can happen for a solar PV installation. It can cover energy efficiency measures. We also have ways that we do this for demand response. And so this type of scheme is really what Recurve relies on in order to make these measurements using meter data, and then assigning value to the savings that we do measure for portfolios that aggregators bring to the table. So this is my last slide, and then I'll pass the baton to Armin. Everything that this entails is done via open source libraries that Recurve, along with other working group members, have created through Caltrack. Caltrack is what comprises the baseline model and the counterfactual. Those baseline models and counterfactuals are created through code that is an open source library called the OpenEE Meter. And usually when we're making measurements now, because we've all lived through COVID, and we know that energy efficiency and demand response and these kinds of programs are not the only thing that change energy consumption patterns, right? If you have a global pandemic, that's also going to change your energy consumption pattern, and it's independent of the program. So we've used comparison groups that we developed through what we call the Grid Meter. And that's also an open source library and is available publicly for people to download and use if they want to use them for their own measurements or their own programs. And then we have other open source libraries like differential privacy that I won't get into now in order to keep data secure and private. But all of these tools are available in an open source framework. And right now, Recurve has reopened up effectively the Caltrack development process through the Linux Foundation Energy. So the Linux Foundation, I'm sure you've heard of it. It's like the Red Hat Linux on your operating system. If you're a coder, you'll know what I'm talking about. But this process is open to the public. It's a working group. We invite anybody, whether they're subject matter experts or not, to come to the table, advise us on how we develop these methods, what the methods need to accomplish, test the code along with us, even contribute if they have the time and space to contribute to the methods. And we've just gotten through an update of the Caltrack daily methods where many utilities out there, of course, don't have AMI data yet. There's monthly and daily data. So the ability to do this kind of a calculation using monthly and daily data is still very, very important. We just updated those methods. And that is being pushed right now into the OpenEE meter repository and being tested, and those methods will be finalized and available for everybody to use. What Armin has been working on and is going to talk about today are the preliminary research steps that we've been taking toward Caltrack 3.0, which will be an update of the hourly methods. And I think one of the things that we've been debating, and we would love people's insight on in this call if they can offer it, is all of these methods and all of these open source libraries rely on traditional modeling techniques. Now, these can be advanced. It's not to say that they're simple, but these are all techniques that can be sort of in principle traced back, and we call those supervised models. But what Armin has been diving into in his area of expertise is on deep learning, neural network approaches. And deep learning approaches offer some real advantages in our minds when it comes to the next generation of programs, because we don't want to limit aggregators. We don't want to limit utility programs to only a specific set of energy efficiency measures, or only demand response, or only battery storage, or only this or that. We are hopeful that the virtual power plants that can arise to satisfy the needs of the grid today and that can scale actually should leverage tons of different technologies. We should have battery storage, we should have solar PV, we should have EV charging, in addition to demand response, in addition to energy efficiency. And when you layer all of those things on top of one another, all of a sudden it gets really hard to just try to model that with a traditional coefficients driven model. So Armin has taken the baton and dove in and tried to understand what's the potential for deep learning models. And where we're starting is on solar disaggregation and an hourly model that can better handle solar PV customers, and on EV detection. Can we use deep learning models to effectively detect customers that have electric vehicles and inform the utilities of who those customers are? And we have some exciting results on both of these fronts. They're not complete, but we have a good start. So I want to pass the baton to Armin here, and he can walk us through. We're going to start with some of the work he's done on solar PV disaggregation. And then if we have time, we'll end on some EV detection. And then we'd like to open it up for discussion and get any thoughts or feedback folks have. So Armin, let me pass the baton to you. And if you don't mind, maybe I'll keep the slides and
sure.
Walk through.
Yeah. Hi, everyone. It's Armin here. I need to run through the slides because we don't have time, and we definitely want to have that Q&A at the end. So I'll try to keep it in the high level, but a little bit of detail and low level for those people who are more technical and just like have fun at the end. So, so the nature of the beast. As Adam mentioned, we have Caltrack 2.0 hourly, and this model is open source and uses time of the week and temperature for modeling smart meter data. That counterfactual Adam mentioned. And this model has been developed by many different institutes, and many people worked on it under Linux Foundation umbrella. And at least we use it in many different projects, but it has its own issues. Because one of the issues that, because we just use time of the week and temperature, we don't consider the main driver of the electricity consumption, and most importantly, solar generation, which is the solar irradiance data. Because we don't use it, we can't perfectly capture it. Although we can have prediction for the non-solar and solar customers at the same time, but for the solar PV customers, we do a fairly poor job relative to the non-solar customers, which I'll show you some figures in the next slide. But one of the main issues of not using solar data is that, imagine we have October 22, 2022 as a sunny month mostly, and we're training based on that data set. And the next year we're going to get a cloudy October, and then there's no way for the model to know we have a cloudy day. The temperature is correlated with the solar data, but it's not enough. And we saw this phenomena in Southern California. We had a very rainy couple of months, but previous year it wasn't like that at all. Can you go to the next slide, please, Anne? So this is the example that I was talking about. So the left figure shows, shows the meter without solar panel. And as you can see, for the most part, the Caltrac counterfactual, which is the orange curve, follows the trend of the observed data. And we have fairly low error, but on the right side, there's a meter with solar panel data. And visually it's obvious that we're not doing a great job. And it's basically due to the cloudy weather. As you can see, those dips in the blue curve are those solar generation. That's why they're negative, they go below zero. But the orange curve shows that those counterfactual, they're not following that. That's basically in the baseline, we had the cloudy days on that period of time of week, but we can't see that in the actual reporting year here. And there's some statistics. The errors is like basically twice for the solar panel customers relative to the non-solar customers. So what is the solution? Solution, as Adam mentioned, is Caltrac 3.0, which we are working on it and expected to be ready by October, maybe sooner, maybe later, it depends. So the primary goal of the Caltrac 3.0 is to have a good counterfactual. So we need to have a great prediction for the AMI data. This is the primary goal. And to do that, we need to use, again, weather, temperature and weather data, and at the same time, solar irradiance to cover that gap. And the secondary goal is to, if we can, is to see if we can separate the solar generation from the building load. And what do I mean by that? I have an example in the next slide. So what is the main problem? What do we mean by solar disaggregation? So as you can see on the left figure, the AMI, the AMI data that we see is a summation of the building load and solar generation signal. So pretty much load minus solar equals AMI. And we don't have access to the sub-meter data for solar or the load for the most smart meters, almost majority of them. And on the right side, you can see the AMI time series or AMI signal that is available to us. And mostly they have this, they don't have any sub-meter, as I mentioned. So we have the load and we have a couple of dips, which means this meter ID has solar generation. It goes to the negative in the middle of the day and goes back to the normal load and so on. Adam, if you. So basically, we want to separate the solar generation from the load or we want to see what portion of that AMI or the blue curve is solar generation, and the green curve is a load, like to separate these two. And to do that, we need to use solar data as a proxy. We are using solar data as a proxy to separate these two. In the Caltrack 2.0, for each area, we had a couple of weather ID, and we extract the temperature and then map each meter ID or each smart meter to the closest weather station. We basically, in the Caltrack 3.0, we wanted to do the same thing, but grab the solar data for those customers, for those solar stations, and merge it with the weather data or the temperature data that we had. And for the current presentation, we use a couple of solar customers, which they have, of course, smart meter data, and they had solar sub-meter data just for evaluation. I want to emphasize here, we're just using AMI data and weather data, so we don't have access to the sub-meter data. But in this case, we have the sub-meter data for evaluation purposes. Now, we don't use it in training or anything else. So quick note here, both in the solar PV disaggregation, mainly in the building load model and EV detection, we're using deep learning model. This figure is just basically a schema of a neural net. This is not the neural net that we're using, but because we tried multiple linear, non-linear models, those like off-the-shelf models, and we didn't get good results. And this is basically for building load models, because we have in the raw data hourly, we have high noise, and the data is very variable. And it's hard to model them with the normal methodologies that we used to have. And for the EV detection, we have, again, dealing with the raw data hourly. At the same time, you need to add some other uncertainty on top of it, which is the pattern of EV charging for different households. And then we need to extract those patterns from the time series. In order to do that, we are using deep learning, some sort of different deep learning procedure for that problem as well. So this is that funny stuff that I was talking about for the technical people. But if you don't understand this, if you don't know this structure, don't worry about it. I'll walk through the whole model. But all in all, the top side, I don't know, Adam, can we have a laser or something so I can show that?
Oh, sure thing. Can you see my mouse?
Yeah, so the top part from the feature time series, and those two blue blocks are basically a schema of the deep learning model that we have for the building load. So we have two modules, one for the load on the top side, and then we have one module for solar on the lower part, which as of now, right now, we have a linear model. So why we choose linear model? Because we tried non-linears. It's a little bit hard to optimize them, but right now we use linear model on what? So basically, solar generation would be equal to effective PV size, which we call it PV capacity right now, and solar irradiance, or GHI, which is global horizontal irradiance, which means if you have a flat surface, what is all of the solar irradiance you can get, either directly from the sun or diffused from a different part of the atmosphere or the location that you are in. And we saw that solar generation has a very high correlation with GHI. So it's a good assumption that we use linear model for GHI. We can improve it. Yes, that's on the future work. So basically, the load part is responsible to unfold the patterns inside of the feature time series, which we have weather time series, such as temperature, relative humidity, wind speed, and so on. And we have some contextual features like time of the day of the week and month of the year. And we can add and reduce these features. But on the top side, we have the load. And then on the lower part, we have the solar. And then these two at each iteration, they talk to each other. And they're trying to minimize a loss function, which is basically load minus solar, which is our counterfactual, or the AMI prediction, tries to meet the observed value as much as best as possible. But at the same time, we're trying to separate the load and solar. This loss function is a little bit more complex. I'm not going to go in detail, but it consists of a mini-square error. It consists of how cloudy is the day, different weights, standard deviation of the load, and observed value. They're playing with each other to iterate between the load and solar and optimize the whole model through the back propagation at each iteration. So we're using normal test train separation in the data. As you can see on the left side, imagine we have the 3 blocks, that's the whole data, and randomly we choose a part of it, put it aside, that's our train, that's our test set, and train on top of other remaining data. We can do that multiple times in a random way. And the summation of the average error on the test side, on the test data, would be our expected performance for the future data set that we have. So basically, we call it cross-validation, but right now, I just want to bring one round of it to see how the model is performing based on one of the train test data set. And on the right side of the curve, we're trying to kind of optimize the structure of the model in a way that we don't have an underfit model, which we are doing not great in the test, either in the train or the test data set. And we don't want to overfit the model as well. In deep learning, it's easy to overfit on top of the training error. You can even bring it all the way to 0 if you have a big enough and more complex data set. But we want to be in the middle, best complexity, and have balance between train and test data set. So in this slide, I brought the very preliminary results for one ID for the train and test set. I just want to compare how these are different. And then I brought a couple of other IDs to see for the other meters. So this is not like a picked smart meter. So what is this curve telling about us? As you can see in the top subfigure, we have 12 peaks of the solar. What do I mean by that? So what we have 12? We have 12 months. And in each month, we have the median daily load shape. So basically for the first month, we got the median of the whole days over there and plotted here. So, and then dashed red curve is the actual value that we have from the submeter data, and the blue curve, the solid blue curve, is the predicted from the current model. So in the first row, we have the solar actual and prediction. So this is the result of the solar disaggregation. In the second row, in the middle row, we have the building load prediction. This is, as you can see, it's way more variable and has more noise compared to the solar, because solar basically follows solar irradiance, and the load has behavioral pattern to it, and it's specific for each smart meter. But the first goal, as you remember, was having a good prediction for the AMI. As you can see, and this is for the train data set. I'll show you the test data set later. But as you can see, the AMI prediction is kind of perfectly follows the actual data. We have more error on the load and solar. Adam, can you just, okay, this one is for the test data set. So of course, for the test data set, we have a little bit lower accuracy, but still, as you can see, for the AMI prediction, we're doing a good job. It's a little bit more uncertain for the load. And if you can see, for example, between 192 to 216, that period, that difference is basically the model is trying to predict this kind of as close as possible to training data set, but test data set in this case is different from the training set. If you go back, Adam, one slide, and then come back in the load side. So basically, that's why we need to do the cross-validation, do that multiple times to have a better idea what is the actual predicted error for the future and data set that we have. So on the left side, we have two tables that summarize the errors for the training and test set for the different parts of these figures. First of all, we need to talk about daytime solar, as the other sides are. Other time of the day is pretty much zero. This is that's a little bit misleading. If you're looking the whole period, you need to look at the daytime for the solar specifically. And as you can see, we have fairly low error, and the test set result is kind of following the train set. So Adam, can you proceed to the next? So this is, I just brought it here real quick to show you that PV capacity, the algorithm tries to converge to the best optimal effective PV size, and the bottom part is the train test error. We don't have that much time to talk about this a lot. So these are these two next slide are for different meter IDs. And for the test data set, as you can see, still we're having a great AMI prediction. But as you can see, even though we are taking the median of a month, still on the load side in the second row, still on the actual load, still we have lots of noise. And that's why, because these are in interaction in the model, that's why we have sometimes over prediction and sometimes under prediction for the solar part. These are the parts that we need to improve in the future. Adam, if you can go to the next slide. So this is for another smart meter ID. Again, AMI is following, but for the solar, we have some sort of shift. And that can be due to the fact that we don't consider the orientation of the solar panel, which one of the things that we will discuss and try later. I tried a little bit, but I didn't get a good result, so I have to attack it in a different way. And you can, as you can see in the beginning, I think that's January on the solar side, the solar is zero. So either we have no solar data over there, or actually in the next month, which is February, they installed their PV panel. So that can be used, this aggregation can be used for the timing of solar intervention, or when they install the solar as well. That's gonna be a use case for this methodology. And yes, so future work and supports for the CalTrack. One of the future works that I really wanted to emphasize on it, the improve the accuracy based on the load to solar ratio. Sometimes for those, for example, commercial buildings that we have 300 kWh at each hour, the solar is, for example, 10K, and then it's hard to extract that solar because these two ratios are way different, and we need to find a way to solve this problem. And as I mentioned, we wanted to use, again, a physical model of solar. It's a nonlinear model, but it has many more different inputs, and the variables are, again, PV size, tilt angle of the solar and orientation angle of the solar. We should do population level model evaluation after we get a solid model for each smart meter. We want to test that on non-solar customers to see if we to make sure we get zero solar output, and we want it to be consistent throughout all of the meter IDs, either non-solar and solar customers. And there's a bigger idea that we have, because solar stations, the number of solar stations compared to the smart meters are basically couple, maybe 10, 20 for tens of thousand meters. We want to encode and decode, use autoencoder decoder for those time series inside of each weather station for the weather time series, and use the embeddings for that, because we train them and the summarized version of those data, and train the models for each smart meter based on those summarized embeddings in order to make the computational time way smaller.
Armin, why don't we spend
Yeah.
maybe just 3 or 4 minutes and give a sneak peek of some of the EV stuff, and then we'll open it up for discussion.
Yeah, sure. I'll try to.
And I'll just give this slide just really quick. I mean,
Okay.
our motivation behind this work is, like we said, and we'd like some feedback on this from folks in the audience. We're not entirely sure that most utilities know who across their grid necessarily has an EV or when they got an EV, which means they aren't focused in their messaging to those customers, and they may or may not have an opportunity necessarily to market specific programs to those customers. And at the end of the day, if we have millions and millions of customers purchasing EVs, it would be good right now for utilities to start understanding what is the impact on the grid when a customer gets an EV. What type of programs should I be offering that can actually impact when customers charge? How can I orient that charging toward times when it is least expensive and lowest carbon intensity? And ultimately, we'd like to also be able to help utilities disaggregate the EV charging patterns themselves using only AMI data, similar to what Armin just showed for disaggregating solar PV consumption. So all of this is, I think, important in our minds to wrap our heads around, and also feeds into just our ability in general to model customers well, so that we can make accurate measurements of demand side programs for customers that have EVs or customers that don't. So Armin has dove into data that looks a lot like this oftentimes. And Armin, why don't we explain what some of the challenges are to this?
Sure. So on the right side, you see AMI data for some period of time for a customer that has EV and solar. As you can see, we're having dip on the negatives. So first of all, solar disaggregation can help this way more. We haven't used it because EV detection project was before solar. So the result here could be even better based on solar disaggregation. And as you can see, the charging pattern is different, and not all of the customers have huge peaks. Maybe you say like, this is a huge peak, it's easy to detect, but not all of them have Tesla charging, home charging level 2. And that a lot of plug-in hybrids or smaller EVs and maybe level 1 chargers, as Adam had in his house. So basically, we have different charging patterns. We don't know the size of the EV. We don't know the charging infrastructure for them. And we just have the utility AMI. How, based on this, we can detect the EVs, Adam? So we had a data set of almost 20,000 EV customers. We knew that they have the EV in their house, and we collected 80,000 other customers that they didn't have EV, and we do the train test split, and the result that you're looking at is for the test data set. So real quick, on the left bottom top part, we have that AMI data, and we try to do the feature engineering based on because we have a huge data set, at least for a year. We needed to summarize it to different feature time series with the feature engineering. These are the 2 summarized version of the curves that you can see on the left bottom figure. And there are many more features time series, but these are summarized. And this is being passed to a big deep learning model, and it tries to map the input to the either you have EV or not. And the result, as I mentioned before, we use different models like off the shelf or any other linear, nonlinear models. And we had the best one had 5,000 misses out of 12,000 samples. But the model that we have already for both false positive and false negative altogether is less than 500 misses. So as you can see in the bottom side, those curves, yes, exactly, EV and clear prediction, that's the probability of that customer that have EV or not. And on the top left, true negative, we have the probability of that customer doesn't have EV for that. So basically, the model, for the most part, trying to push these two categories as far as possible. But for some of them in the false negative and false positive, you can see still we have some errors. And based on the analysis me and Adam and Travis did before, couple of those false positives that actually had EV, but we labeled them as non-EV. So there's some filtering is needed for the future analysis.
Thank you, Armin. Great stuff. Just one little note on this graph down here. If you're at a utility, what we're basically saying is when a customer has an electric vehicle, most often we are quite sure about it. If you look at this y-axis, we're talking about counts up to 1,250. Oftentimes, when the model, when a customer has an EV but the model misses it, we're actually wind up in kind of a model territory where we're less sure. So one of the things we would probably recommend doing is saying, look, if the model winds up kind of in a gray area, or if you wind up with a very clear EV prediction, these are the customers on your grid that have EVs. And so if you're at a utility and this would be useful for you, I think what we're looking for now is a partner to say, let's try this out. If you don't know necessarily who has an EV, or you want a detection of it and you want to try to market to those customers for a program to help them manage their charging, reduce their bills, help your grid, we think we have a model that can do this already. And we would love to work with you to refine it even further. So let's open it up for discussion. I know we just have maybe 5 or we can probably stay for an extra 5 minutes if folks have the time. And are there any questions that folks have, or any feedback on anything that we've covered today around solar modeling, disaggregation, EV detection, or just the broader concept of demand flexibility and modern programs in general that need to be modeled?
Adam, it looks like there's a question in the Q&A.
Yeah.
I think I can answer that.
Yeah, go for it. You want to read the question? Let's read the question. It is, is the input data for solar generation from all California or over the USA?
It depends. Right now, our test cases were just in California, and we had a small test case. So I think it doesn't depend on California, or it's based on your location. So if you're in Arizona, we're trying to get the data for Arizona. And no, GHI is not a constant value. GHI is a time series, but we multiply it by a constant. That multiplication to the time series shows the time series solar generation for that location. And how many years of data are used to build your model? We can shrink it to a month or a year. Right now it's a year. Because I just wanted to show that median daily of each month for this presentation. I tried it for 3 years of data. And one thing that I forgot to mention, for the solar disaggregation, we're doing almost a minute per meter ID. That's the whole computational time. And we're trying to reduce it, but as of now, it's fairly okay, very good. But if you use 3 years of data instead of 1 year, that 1 minute would be 2 minutes. It's not linear, but it's a little bit more computational time, but you get more robust results. Adam, you're mute.
I've got a kid babbling away and crying in the background, so sorry about that. Just mute myself. Are there any other questions, or is there any feedback? Bob Ramirez, do you use the CalMac weather data? Or good question, Bob. Yeah.
So for the temperature for Caltrack 2.0 right now, we're using NOAA dataset temperature, which is free. But for the solar data, for the test right now, we're using NREL dataset, but till and we have the data till end of 2021. But if you want to analyze 2022 or 3 or anything recently, we need to use paid dataset, which is, for example, weather data, weather.com, Solcast, or a bunch of other companies out there. It depends on the pricing. So,
yeah. Well, let me just say, we are about to embark on Caltrack 3.0, which is going to be a public working group through the Linux Foundation Energy. And we are looking to advance the models that Armin has started to build on and get advice from subject matter experts and stakeholders throughout the industry through that working group process. I think Sabrina will look to follow up just with the attendees and the webinar audience with more details there. We would definitely invite you to join that working group, lend your ideas, lend any even work or data that you could to that effort. And when it comes to the EV detection stuff, if somebody's ears are ringing on this call, and you say, hey, you know, we might have a chance to work with some of this or work with Recurve to develop this further, and we would like to use it to help identify customers on our grid that we would, you know, potentially understand their load impacts of getting an EV or understand how to market to them for specific programs, then we're very open to those kinds of partnerships, and we would definitely encourage you to reach out. Well, let's answer a couple more questions here real quick that are coming in through the chat. Where do you get building size data? Is that information important for your model? Building size data is typically not used in our models, like square footage and things like that. We don't typically even get it. And oftentimes we find that it's actually kind of a proxy that we have better information that we can glean from the building's consumption itself. We oftentimes look at how a building is using energy, not just in sum total, but in proportionality to other buildings, things like that. So we'll look at a building and we'll say, how much cooling energy are they using, but also how much cooling energy are they using relative to their total consumption. And those are the kinds of patterns that help us identify customers for utilities to target for air conditioning programs, for example. Brian asks, more macro level question. For a map aggregator, any advice on sub-metering for customers considering adding solar in addition? Good question. I think if customers and working with their aggregators can sub-meter solar, then it gives us the ability to be more confident about the model that we're generating. And we can build a model potentially directly on the building load and remove the solar directly. So you don't have to do so via a model, but you can do so via, you know, 0% uncertainty ETL step effectively. So definitely ping us with further questions on that front, Brian, if that's something that you're considering, and we'd love to talk with you. With that, I think we're 2 minutes over. And please do,
there's
like I said, reach out. Yeah, Armin, please go ahead. Mm-hmm.
There's one more. So what data other than AMI is needed for the EV determination, for the EV detection? Nothing, just AMI data.
Just
right?
AMI. That was the whole challenge. Yeah. We were just trying to say, can we do this? Because oftentimes a utility will know, like I said, who has solar, and will just have a flag like this customer has solar, this customer doesn't have solar. But with an EV, we're unsure, or we actually think like that data may not be as available or as reliable or as comprehensive. So we're trying to see purely based on AMI data whether or not we can identify the EV presence.
And it's EV detection, and it's not EV disaggregation. So
not yet.
Who has the EV? Yeah, that's a way harder problem.
Yeah, and like I said, we would love to work with anybody who's interested in either of those problems. The EV detection is a first step in our minds toward a broader model that can reliably disaggregate EV charging patterns as well. Okay, everyone, thank you so much. Good webinar. I hope it was useful for you. It was at least fun for us. And please, like I said, reach out if you want information about the CalTrack working group, if you want information about either of these models, or you have perspective ideas about how to advance these things, or you'd like to partner on any of it. We'd love to hear from you. So thanks again, and we'll see you next time.